In this video, we're going to continue to talk about sampling distributions. In the last video, we talked about the sampling distribution for P, or P hat rather, okay? The sampling distribution for the sample proportion. In this video, we're going to talk about the sampling distribution for the sample mean, okay? And for the sample mean is X bar, okay? That's the symbol for the sample mean. And here we have that the sample mean, the sampling distribution of the sample mean depends on the sample size, n again, okay? And so actually, we're going to define two different situations for the sampling distribution of X bar. When the distribution of the data, that parent population, is normal, and as an example, X, I have that X here is normally distributed with a mean of mu, standard deviation of sigma. Okay? When X is normal, then the distribution of X bar, which is the sampling distribution, is also normally distributed. Okay? And it's normally distributed with a mean of mu and a standard deviation of sigma divided by the square root of n. Okay? Now remember that mu and sigma come from the parent population. Okay, so that situation is nice. So that's the situation that we hope we're in. But oftentimes we won't be. We'll be in a situation when the data is not normally distributed, or we may not know what the distribution of the data is. Okay, so if we don't know what the distribution of the data is, when the data is not normally distributed, then we have that X bar is approximately normal with a mean of mu, standard deviation of sigma over the square root of n. Okay, and so you may say, well, that's the same thing, and that's true, but the second one is approximately normal. The first one is normal. So there are slight differences, and the big difference is that situation 2 has a condition with it. Situation 1 does not, okay? That's always true. Situation 2 is true only when certain conditions are met. The condition that needs to be met here is that n needs to be greater than or equal to 30. Okay? And the idea behind that condition is from the central limit theorem. Okay? And so we're going to talk about what the central limit theorem is here in just a second. Okay? So situation 1 is always true. Situation 2 is only true when n is greater than or equal to 30. Again, this is not a hard and fast rule. Okay? N greater than or equal to 30 is not a hard and fast rule. It's a suggestion. Okay? But it's a suggestion that we're going to follow in this course. So if we go back to our Rice virtual show, okay, and you look here, if my parent population is normal, so this is about a mean, so this is a sampling distribution for the sample mean, okay, if I have a normal population, it does not matter what the sample size is, the distribution of the means will always be normal. So let's do that. Here I take a sample of size 2, okay, sample of size 2, and I can animate that from a normal population. If I do it a bunch, okay, then I'll slip and do 100,000 times. You'll see that the distribution is normal, okay, no matter we have a parent population and this sampling population. They're both normal, which is great. Now, if I say instead of having a parent population that is normal, I have one that's called uniform. Okay, so we'll see the uniform distribution here. Okay, if I take sample of size 2 from the uniform distribution, what I'm going to get, if I do this 100,000 times, is something that is very not normal. Okay, this in fact is called the triangular distribution because it forms a triangle. So that first thing that I showed you was situation 1. This is situation 2. Okay, so it's certainly not true that this is normal. I can sort of fit a normal curve on that, and it certainly does not look normal. But if I increase the sample size to 5, and I hit 100,000 times, you see it looks a lot more normal than 2. Okay, it still doesn't quite get there if we increase it to like something like 20 or 25, and then we hit 100,000 times. Then it looks very normal. Okay? So that's what the idea behind that second situation is. So, and that has to do with something called the central limit theorem, which is probably the most important theorem of any theorem in statistics. So it's one of the most important, if not the most important. The central limit theorem, or a central limit theorem, is actually a class of possible theorems that say something about how averages behave. And so you might say, well, why are we so interested in averages? Aren't there more things out there than averages? Yes, there are. Okay, but it's usual, or it is usually common to be interested in the average, okay, because it tells us something about maybe like normalcy. In statistics, we're often interested in the average. If we can say something about the average, then we can say something usually about the whole situation. So, a central limit theorem is a class of theorems that say something about how the average behaves, or about how averages behave. Okay, both the sample mean and the sample proportion are averages. Okay, so mean, of course, is an average. Okay, but the sample proportion is also an average of sorts, and so it falls under this class of theorems. There are many different central limit theorems. There's not just one, as I've been saying here in the slide. The central limit theorem that we use, okay, the one that we're going to use in this class, is called the Lindeberg-Levy central limit theorem. Okay, and so I make sure to mention those names because actually in your reading that you have this week, they'll talk about Lindeberg-Levy type stuff. Okay, so these are two people, one named Lindeberg, one named Levy. But this is the version that we talk about in the class is the Lindeberg-Levy one. Okay. So here's an example. According to the 2010 Census Bureau Current Population Survey, the average number of people in family households that contain both family and non-family members is 4.43 with a standard deviation of 2.02. Okay, so that was a lot there. I'm saying that the average number of people in a family household is 4.43 with a standard deviation of 2.02. Okay. Suppose that I take a random sample of 225 people. I want to know what is the sampling distribution of X bar and what's the probability that I would see a mean of at most 4.2. So for continuous questions like this, okay, or for seemingly mean questions like this, okay, and not ones that are like not nice to you, but ones that involve average or mean, okay, and this one says the average number of people, I have to look at the first two, or sorry, not first two, I have to look at the two situations that this could possibly be under. The first one is when the population is normal. But nowhere in this example does it actually say that the average number of people in a family household that contains both family and non-family members is normal. It just gives you a mean and standard deviation. So you have to go with situation number 2, where you don't know that the population is normally distributed. Okay, so Is 225 greater than 30? The answer is yes. And so x bar is approximately normal with a mean of 4.43 and a standard deviation of 2.02 divided by the square root of 225. Okay? And then again, you can use that distribution to answer the probability question below. Okay? Again, I'll post the answers to this on D2L, okay, and point you towards them. So here's your turn. I give you another example. I ask for the sampling distribution of x, and I ask for what's the probability that you would see a mean of at most of 2.75 from my sample of 200. Okay, so there's the your turn for this video, and this marks the end of Chapter 7, Sampling Distributions.